Okay. Now, today's lesson that I'm going to cover is the last lesson, 3.2, that will be included on test one. So test one will include everything through today, except it does not have questions from the algebra review. So starting from lesson 2.2a up until today. The test is due a week from Friday, so September 25th. Now, that is just the due date. You are allowed to take it sooner. The test is password protected, and I will be sending a Canvas message to all of you telling you what the password is. The reason why it's password protected is the test is timed at 2 hours. Once you enter the test, the clock starts and it will not stop. So if you enter and then leave, the clock is still running. So the password is just so you don't accidentally enter the test before you're ready to actually take it. So you want to make sure to set aside a block of time, sometime between today and the due date, the 25th, but you can take it. Now, okay. I want to show you something in Hawks. Okay. All right, I'm going to share my screen in just a second here. Okay. Okay, so this is the same kind of a view in Hawks from the main page that you all have. So you see here that the test one shows up here. Now, chances are on your list, practice test one will also show up. It doesn't show up here on my list just because, just as for testing purposes, I already went ahead and entered it. But you can always see all of the assignments that we have by clicking here. So here we have everything. So all the lessons and all of the tests, and including things that have been done. So somewhere on your list, or you can always look under web tests and just see what tests you have. So there's 6 tests altogether, but really there's only 3 that count towards a grade: test 1, 2, and final. Then each one is paired with a practice test. So here's practice test 1. Each practice test, like I said, it's optional, does not count towards your grade, is an exact copy of the real test, except obviously some details would change, like numbers, etc. So there's some randomization in there, but you really do see what you're going to get. So a practice test does not have a password. It has an unlimited number of attempts. So I urge you to make the centerpiece of your test preparation taking the practice test. In fact, I would suggest go through it once and then if you can go through it a second time, subjecting yourself to the time limit. So see what it's like to go through all problems and doing them in that amount of time. So at least that way you can make sure that you work through these problems fast enough. Do yourself a favor. Be sure to go through a practice test before you take the real one. Okay. But so sometime later today, maybe tonight, you could expect a Canvas message that has the password for a first test. Okay. So when you click Start Test, that's when it'll prompt you for that password. Okay, so now we have just this one lesson left to cover. Okay, so there's one more differentiation rule that we need. And it's called a chain rule, and then a special case of that is the general power rule, which relates to the power rule that you've already been using. So first, I'm going to take a moment to talk about these two rules, and then in these problems, I'll show you how those rules are used. Okay. So we know how to take a derivative of certain combinations of functions. So for instance, you can do f of x plus g of x, or minus, really no different. That's these are the easier ones. Okay. You also know after last lesson how to do a product of functions. That's a product rule. And then a quotient. That's a quotient rule. But there's another combination we need to look at that is called a composition of functions. So that would be f of g of x. Make sure you do not confuse this with a product of functions. What you do is you evaluate g of x first. The result of that is substituted into f of x. So examples, like we have, and we'll see several examples in the problems, but I'll just write a couple anyway. So x plus 5 raised to the 4th power. So in this case, x plus 5 is the inner function. And what is done to it? After you evaluate x plus 5, you're plugging into a function that raises to the 4th power. So then that's plugged into a function f of u equals u to the 4th. So g of x is playing the role of u that gets substituted in here and raised to the 4th power. I'll do another one. Let's see. Okay. All right. All right. So in this case, that should be x squared over here. All right. So in this case, the inner function is square root of x squared plus 1. The outer function, so what is done to this expression once it's evaluated? It's substituted in here and cubed, so we have u cubed, minus 4 times g of x, if it's 4u, plus 10. All right. So here we have, you evaluate the inner function first. The result of that is substituted into the outer function. Right. So once you recognize, and like here's another example here. What's in parentheses, that's the inner function, that's for g, and it's all of that is raised to the 2/3 power. So once you have a composition of functions, we have a differentiation rule for that called the chain rule. So what is that? The derivative of f of g of x. what you do is, first, whatever the outer function is, we take a derivative of that, so f prime. But you substitute g into f prime, just as it was substituted into f out here. All right. Then you multiply all of this times the derivative of the inner function. Okay. So derivative of the outer evaluated at the inner times the derivative of the inner. As an example, I'll do. Okay. I'll make up a more interesting one. And we'll see several more examples through the problems, but okay. Let's say we'll take the raise it to the 1/2 power. So x squared minus 5x plus 6 to the 1/2 power, where the inner function is what's being raised to the 1/2 power. So x squared minus 5x plus 6. And then the outer function, f of u, would be u to the 1/2 power. Okay. Now, when I was showing you product and quotient rule, I recommended that you line up all the pieces of what you need for derivative, like getting your ducks in a row. Same thing here. You, after you identify this is your inner function, this is your outer function, you need both derivatives. So again, getting your ducks in a row, we need g prime of x. So that'll be the derivative of this, which would be 2x minus 5. And then f prime of u, we just use the power rule in that. So that is 1/2 u raised to the minus 1/2. So now we use these to come up with the derivative. So that'd be h prime of x. So our original function is labeled h. So that's f prime of g of x, g prime of x. So that would be f prime but what is plugged into f prime? It's g. So wherever you see u, that is where g should go. Not g prime, the original g. That's a common mistake, that you take the original you take the original inner function, plug it into the derivative of the outer function. So I go back up here, x squared minus 5x plus 6, and that is substituted for u. Use parentheses. Remember, parentheses are your friend. Then all of this is multiplied by the derivative of g. So I have that handy. Again, use parentheses. And you're done. So you have a function like this that's a function of a function. Pick out your outer and inner, take derivatives of both, and then in here, the derivative of the outer one, take the original inner function. That is what u is in this case. So you don't have any questions about getting this derivative? Be sure to unmute yourself if you do. Okay. Now, one instance of a chain rule is called the general power rule. So really all it is it is a chain rule where the outer function is always raising to a power, like we have here. So if I review for you the power rule that you've been using, so that says that the derivative of x raised to some power is you pull the exponent down, you raise x to a power 1 less, and you're done. Now, so if you combined with the chain rule, we have what is called the general power rule. So the general power rule covers a case where you have some function being raised to the nth power. Here it's just plain old x. But if you have something else raised to a power, what's the derivative in that case? So it's very similar to the original power rule. So now you have f of x raised to the n power. Okay, so it starts out the same way. The exponent comes down, then you have whatever you're raising to the nth power is now raised to the n minus first power. So far it looks exactly right like the power rule. You just have f of x in place of x. But because you have f of x instead of just plain old x, by the chain rule, you must multiply that by the derivative of whatever is being raised to the nth power. And that's exactly what happened here in this example. This is actually not just a chain rule, it's an instance of the general power rule. And look at a derivative. It's 1/2 times the inner function raised to a power 1 less, so minus 1/2, times the derivative of what's being raised to that power. In fact, these two rules really are saying exactly the same thing. This is just a special case of this, because if f of x is just x, well, its derivative would be 1. So there's an implied 1 here. So all of these problems that we're going to see deal with the general power rule. But you have a function, some kind of function being raised to a power, and this is what you need to do to take the derivative. Okay. So now we'll step through these problems and make use of the general power rule. I should mention that this lesson has several problems that are worded this way: find a derivative, write your answer using positive negative exponents instead of radicals. And the problem involved may not necessarily have a radical in it at all. So in that case, you can just ignore that. They're just giving the same directions for every single problem, no matter what function is actually given here. Okay, so here we apply a general power rule where, so this rule, where your f of x in this case is, well, it's being raised to the 2/3 power. So minus 6 x to the minus 3 plus 9x plus 8. So what the general power rule would give, like I was just doing in the example, the 2/3 comes down, and then this function as is, do not do anything to it, not yet. So that comes down here, and it's raised to a power 1 less. So 2/3 minus 1 would be minus 1/3. And then the last thing to do over here is you're taking the derivative of whatever was being raised to a power in the first place. So for that, we're using just an ordinary power rule for this term. So we have minus 3 times minus 6 is 18. Then we deduct 1 from this power. It's minus 3 to begin with. So now we have minus 4. And then here we have just a coefficient rule. 9x gives a derivative of 9. And then we get nothing from the 8. And you're done. So you can just leave it in this form. There's no need. There isn't really anything you could do, and that's practical at all to simplify it. So you can just leave it like this. So remember um, remember the steps that we just like before with other functions, several functions you've had already where you have to use a power rule. Bring exponent down. Whatever is being raised to that power as is to one less, then take the derivative of this and put it out here. So a very common mistake is, for example, taking a derivative of this prematurely, or just forgetting to do this part. Okay. Okay. So now that I've stepped through a couple of these, or one problem of an example, a similar example, I want you to take a crack at this one. So who can tell me, and you can just go one step at a time, what the derivative would be?
Put the 4 in front, and exponent will be 3.
Yeah, so 4 comes down. Okay, yeah, the exponent will be 3. And then what?
Okay. Then you have 16x. That's about it.
Yes, that would be it, because the -6 would not give you anything. And yes, that is exactly what we have here. So 4 comes down, and then we have this raised to a power 1 less than before, and then derivative of that gives 16x. Now at this point, there's a little bit you could do just to clean things up, like because you may have you may have an exponent out here. Whatever you have here, you could put it together. I wouldn't call this a requirement, though. And in fact, when it's written this way, it may not be in its simplest form. But for example, if I had to review it for partial credit, like if Hawks marked it wrong, it's actually easier for me to, if there is a mistake, see what he did when it's written this way. But yeah, you can take a 4 and a 16x and multiply them together, and so that's the answer, as simplest as you can get it. Okay. All right. What would this one produce? What would the derivative be in this case?
Would it be negative 18 and in parentheses 7 minus 3x to the 5th power?
Okay. Well, sorry, could you repeat the first part of that answer?
Would it be if the derivative would be negative 18 and then in parentheses 7 minus 3x close parentheses to the 5th power?
Yes. Yeah, the first time I didn't catch the negative. Yeah, so 6 comes down, this raised to the 5th power, times a -3. And yes, but by putting all of that together, you get to -18. So, yep, very good. Okay. Here, okay, this one's a little bit more involved. Although, again, same procedure, and the fact that there's a negative exponent doesn't change anything. And what I would suggest is, okay, so I'd like someone to lay out a derivative in this case. Don't bother doing any simplifying here. So we'll just go one step at a time and verify it from there. So for this function right here.
Are you asking for the answer?
Yes, I am. Yes.
Is it gonna be the whole problem's negative, so negative 30t plus 20 over parentheses 3t squared plus 4t close parentheses to the 6th power?
Okay. To help everyone else see where the answer comes from, I want to do it without multiplying things out at the end. And that way it's easier for me to confirm.
So you just want it not with a division sign?
No, I mean, I saw what he did was after you worked everything out, you did like here where you got this, and then you actually carried out the multiplication. I'm asking, don't carry out this multiplication because that way we can see the individual pieces of the answer.
So would it be negative 5 parentheses 3t squared plus 4t close parentheses negative 6?
Yep.
Or the exponent negative 6 times parentheses 3 times 2t plus 4 close parentheses?
Yes. So that way we can see where all the pieces of the answer come from. Yeah. So -5, and then all that to the -6 power, and then you take the derivative of that, which, unlike the previous examples, would have two terms. That we see here, 6t plus 4, and then you could multiply this out afterwards. Like you could take the -5 and distribute it through the 6t plus 4, although it's not required.
So if in a problem like on, I forgot the name of it, but where we do our math assignments, if we went all the way down to where I divided it, would that be considered wrong since it's more simplified?
Oh, you mean like if you put this in the denominator?
Yes.
Raised to the +6 power.
Yeah, positive 6 power.
Yeah. It should mark it right.
Okay.
I just wouldn't recommend taking a time.
Okay.
Yeah. Well, from what I found in most cases, because determining if two mathematical expressions like these functions are equivalent to each other, and actually programming a computer to do that is actually not easy, just because there's so many different ways to rearrange an expression. And so it all depends on how sophisticated the software turns out to be. Most cases, I've found that Hawks does properly detect when, so we've already talked about a few different ways in which this function can be written. It does pick up on things quite well, but there is a rare instance where a student will tell me that Hawks marked a problem wrong. They'll show me their answer. I look at it. It's like, yeah, I've looked at this a zillion times. It is right. And I can't see anything like a formatting error that the student did. So you never know. But that's why I encourage you, if you think that Hawks is not evaluating your work correctly, that I can always intervene. And I'll just do that intervention preemptively on tests. But if it happens on homework too, you can ask me about that. Okay. This function. Now this will work out the same way as the previous ones, but before we begin, we need to rewrite this function in a different form. So how should this function be rewritten before we even go about taking a derivative? So what function is this equivalent to? Yeah, so if we take this 8x cubed plus 7, raise the whole thing to the 1/3 power. So we do that first before taking the derivative. And then once you have it in that form, then you can apply the same old general power rule. So bring the 1/3 down, this expression raised to the -2/3 power because we're subtracting 1, and then taking a derivative of what's inside. Here there's a obvious opportunity to simplify a bit. You can combine a 1/3 and a 24 to get 8, but again, not essential. All right, so whenever this is why Hawks puts in the directions write your answer using exponents instead of radicals. So so apparently that means that Hawks would not like it if you could take this function here and rewrite it in terms of a radical, but Hawks doesn't want you to do that. So, and again, definitely don't take the time. So just leave it like this. Okay. This next one is definitely leveling up in terms of problem difficulty, because you can see here that you have a function raised to a power, and you could apply the same general power rule to this, but that's not the entire function. You have this whole thing to take the derivative of. So it's actually necessary to use the general power rule, but not just the general power rule. You actually need to use that rule in conjunction with one of the other rules that we've seen so far. So what other rule for taking derivatives do you need to handle this case?
Product.
Yes, this is a product. So here's the first function. And then this whole thing with the cube included is the second function. So what that means is you have to use a product rule first. And then while that's being carried out, the general power rule is needed when you need to take a derivative of this part. So what that looks like. All right. So here we have this function as is. So using my notation from last lesson for the product rule, so P of X would be this first part, and then Q of X would be the second part. Okay. And then the derivatives of the individual pieces should just be a prime. Okay. All right. So here we take the derivative of this piece, and here the parentheses are not absolutely necessary, but it will be needed later, so I'm just going to leave them. So here we have 8x to the minus 3. Oh, didn't like that. Okay, 8x to the minus 3 minus 3 for that part. And then here, so for this one, this piece, the general power rule is needed. So you bring the exponent down, and then what's being raised to the third power untouched deducts 1 from the exponent, and then take a derivative of what's inside. So after that, here the general power rule has been used, and then you put all the pieces together for the product rule, just like last lesson. So here we have Q times P prime plus P times Q prime. So all of that goes down here. And then, okay, all I did here is like I just took this constant and moved it out front. The only other simplification I would imagine doing is like taking a 3 and distributing it through a 12x plus 4. But again, not necessary. All right. So the point here is that once in a while, it is necessary to use the various differentiation rules you've seen in combination. So first and foremost, this function is a product. That's why the first thing you use is the product rule. It's just that because the product rule calls for taking a derivative of the first piece and the second piece, when you get to that point, who knows what you're going to have to use, because these pieces can be anything. So, like, what if this second piece here happened to be a quotient? You would need the quotient rule for that. So you just keep drilling down and taking derivatives of whatever pieces you need, using whatever rules you need. But the important thing to recognize is this is still the product rule. No different than much simpler examples that involve a product rule. It's just that there's more work involved in getting all your ducks in a row. So any question about that fairly nasty one? Again, leaving it in this form, as far as Hawks is concerned, and certainly as far as I'm concerned, is perfectly fine. And in fact, when you do it like this, just leave it like this. If, God forbid, there is a mistake, it's easier for me to see where the mistake is, and generally that will result in more partial credit. The partial credit on tests can be significant. I've had it happen where after I go through someone's test and seeing what partial credit I can justify giving, sometimes the scores go up fairly substantially. I've had it happen where like someone's percentage will go up by like 20 points. And that's why it's important to at least attempt all the problems, because if you don't attempt it, then there's nothing I can do as far as partial credit is concerned.
Action.
Yes.
So on this is in the same chapter, it's the product in Quotient and it's one of the problems I still don't understand. I don't know if we're gonna go over it or not.
Okay, wait. Sorry, which problem again?
I don't know if all of our problems are the same, but it's question 10, and it's finding the marginal revenue.
Okay, so from a previous question. Okay.
But it's from 3.1 product and Quotient rules.
Yeah, I'm pulling it up. Yes. Marginal revenue. Sorry, it's taking some time to load for some reason. Okay, mine's numbered a little differently, but yeah, okay. But there is just one problem involving marginal revenue. Okay. I assume you're right now. The only thing you can see is the current lesson, but let me flip over to that real quick. Okay, can you see the marginal revenue problem now? Please let me know.
Say that again.
I just wanted to make sure that you can see the marginal revenue problem in front of you.
Yes.
Or from my screen. Yeah. Okay, so yes. Okay, so this is a problem. So what was your question about it?
I don't understand it. Like, I did the problem like 11 times and got it incorrect.
Okay. I mean that I can make sure that you're at least following the right process. So whatever function you were given here as of a demand function, you multiplied it by x first.
Yes.
Okay, yeah. So you need that to get the revenue function in the first place. So you would have gotten something like this, except with different numbers. Okay, and then all right. So here we have the quotient rule being carried out, but here taking the derivatives of a numerator and denominator individually, and then so here we just so in other words, you were able to work other problems involving a quotient rule and have those go fine, but then just couldn't get this one.
Yes.
Okay. Now it might be something where so in this case here all I'm doing is applying that same quotient rule that evidently you know how to do. Now what happens with this particular function is that when you simplify the numerator, that we do get some cancellation of terms, and then you just are left with a number up top. The only thing I can think of is that there might be some algebraic mistakes that's happening, maybe something involving signs or parentheses. And so I would encourage you to look over this problem, at least see if you understand how this one is being worked out. Also, you're welcome to contact me directly, and show me what work you did, because I could just look at it and point out the mistake.
Okay.
Okay. All right. Flip back to the other. Okay. Let's see, we have a question in the chat. Okay. All right. To answer a question in the chat, you only enter it once. The answer. So, like, once you got to this point, you just go ahead and enter that, and you're done. It was just rewritten here as a more conventional way of. It's sort of a convention when simplifying answers. If there's any constants in the middle, like here we have a 3 sitting here, just to move those out front, because sometimes expressions like these will have a bunch of constants as factors, so then you just multiply them all together and stick them out to the left. But that's just kind of like a formatting convention. It's not something that any of you have to follow. So what I'm highlighting here, enter that. That will be fine. Any other questions before continuing? Okay. All right. Now there's a problem like this next one in the product and quotient rule lesson also, where so this shows here's the minimal amount of information needed to evaluate the derivative of a function raised to a power at a certain point. So in this case, x equals 4. So if we look at what's involved taking a derivative of some unknown function f of x that's all cubed, then the derivative through the general power rule would be, okay, pull down to 3, then you have f of x squared. Actually, going to move that exponent out here. Okay, and then times f prime of x. This is just what the general power rule would give you. And then but you want a derivative at x equal 4. Okay, so then you just go ahead and substitute x equal 4 throughout on both sides. So what we see is that the derivative of so here we need the value of at x equals 4 of the original function that's being cubed and its derivative. So once we have these two pieces of information, we can just go ahead and fill those in, and then get your answer. Just as like when you have a product rule and you want to evaluate the derivative at a certain point, whatever two functions are being multiplied, you need the value of those functions at that x and their derivatives at that same x. Right, but yeah, really, how you work this out is no different than before. Just use the general power rule and then plug in the x throughout. This is another example that's like one from a couple problems ago, where the first thing you should do, all right, so here's just the same function repeated, and then we rewrite it. First, we take a square root, rewrite that as raising to 1/2 power, but that's still not suitable for taking a derivative. We need to have this expression up here in the numerator. So you go ahead and put it there by negating the exponent. So now it's in a form where you can take the derivative, in this case using the general power rule. So what that would give you is if the 2 is just hanging around there, then the minus 1/2 comes down, and then this expression raised to minus 1/2 minus 1, which is minus 3/2, and then you multiply it by its derivative, 3t squared. Notice the heavy use of parentheses. So be sure to follow that so that you don't have careless mistakes. Sorry, Teams is being uncooperative right now, as usual. Okay. All right. A little bit of simplification can be done here. For instance, the 2's cancel, and then what's left is a minus 1. It can be multiplied by the 3t squared. There isn't really anything else you can do to simplify it. And then we're done. Okay. All right, now we get into the lovely word problems. So here we have this function that models a population. You've had problems exactly like this in previous lessons. It's now that you have more differentiation rules available, they can use a wider variety of functions to put here. So here we have a function of a function. This whole 40 plus 3t, the whole thing's being squared. And so you'll often have problems like these that come in two parts. The first part calls for just evaluating the original function that's given at a certain point. So here, it's t years from now, so will the population be in 6 years? So it's going to substitute t equals 6 in here. So there's your function. You just go ahead and fill in t equals 6 and turn to your calculator and get all that worked out. And then the second part of the question, find the rate of change in 6 years. So you're always looking for the question is you have to ask is, what is it you're really looking for? What function are you supposed to work with? And if the question is talking about, how fast is something growing? How fast is something changing? That's talk about a rate of change. That's what calls for a derivative. So here, P of 6 is what's needed to get the actual population. Rate of change of population, that is P prime of 6. So to take the derivative, first and foremost, this function is a difference of functions. So we have this part minus this part. So then you can take a derivative of these two pieces individually and subtract them. But to take a derivative of a first piece, that calls for a general power rule, and that's what we see here. So we have a 30, then a 2 comes down, and we have 60. Then it's 40 plus 3t raised to the first power. Oh, there's a mistake here. No, oh no, there's not. Oh, typo here. That should just be a 3, not a 30. Okay, just like it is here. Okay, so the derivative of this is 3, so that is what gets multiplied here. And then the derivative of this first part is complete. That's what we have right here. But then you have to move on to the rest of it, the minus 1500t, and take a derivative of that. But that's just coefficient rule, and that's what gives you the minus 1500. So this will often happen is that you're working on taking a derivative of some complicated function, and that calls for taking a derivative of certain pieces of it. And in taking a derivative of those pieces, you may have to use any of the other rules that you've seen. So in this case, a general power rule. Okay. Now, here, just a little simplifying because you're about to plug in something for t in here. So now you go ahead and substitute t equals 6 throughout, and then just let your calculator do the rest. So in terms of units, this is population. So the first part, the answer, units for the answer would just be people. So the total population will be 91,920 people. The rate of change in population will be people per year. So the population is adding 8,940 people per year at this point in time, 6 years from now. Okay. Next, we have this function, and that's a level of pollution. So it's asking how fast is the level changing after 4 days. Now, t in this case refers to days. So what's needed is f prime because it's not asking what the level is; it's asking how fast it's changing. So it's a rate of change. So you need f prime at t equals 4 because it's after 4 days. So what you do first is rewrite the function in a form that is conducive to taking a derivative. So we have the numerator from before, and then the denominator is rewritten this way. So we use a 1/2 of a square root, and then because it's in a denominator, we write it as a negative exponent. So now you go ahead and take a derivative. But what do we have here? We have this function times this one. So like we had in a previous problem, the product rule is what you use first. So which rule do you use first? It's basically the outermost or final operation. Like if you were plugging a value of t into this function, you'd work out this part first, then you'd work out this part. And what's the last thing you do? You'd multiply those pieces together. So the last thing that's done in terms of evaluating a function is the first thing you pay attention to when taking a derivative. So first and foremost, we have a product. Product rule is what we use. So what happens here is our actually I'll go ahead and mention the pieces. So your numerator is 450t squared, and therefore its derivative is 900t. And then the denominator, but now it's the second half of a product. So that'd be t squared plus 11 raised to the minus 1/2. And then its derivative minus 1/2 t squared plus 11 raised to the minus 3/2, so you deduct 1. And then you have 2t, the derivative of t squared plus 11 that sits inside. Right. So now these are the 4 pieces that we put together to get the derivative. So here we have q down here times p prime down here, so that's 900t. Plus, because it's a product rule, and then we have p here, and then q prime is what goes here. It's just that in order to get all those ducks in a row to use a product rule, you need to use a general power rule along the way. Now, ultimately, you want to plug t equals 4 into this derivative. So it might be a good idea, in this case at least, to do a little bit of simplifying if you can. So here we have 900t. Here the 2's cancel. And then we have, what's left is we have minus t times 450t squared. So that can be condensed a little bit. So we have minus 450t cubed. And there isn't really anything else. There's not really any point in trying to simplify any further. So now you have your derivative, but what the question is asking for is the value of a derivative at t equals 4. So then you go ahead and substitute in 4 throughout. Again, this is why parentheses are very important, and that should be reflected in whatever you end up punching in on your calculator to evaluate this expression at t equals 4. Excuse me. And retaining several decimal places, this is what you get. The problem asks for nearest whole number. A lot of times they ask for rounding to 2 decimal places, but in this case, it's rounding to the nearest whole number. In this case, it's 47.54, so you're going to round up. So that's so 48 is what you would actually enter into Hawks for a problem like this. That problem was kind of nasty. Any questions about that? But you can see that since functions could use various combinations of differentiation rules, it would be possible to come up with something that is quite heinous. Now, that doesn't actually happen in Hawks, but you get an idea of just how messy it can get. All right. Here, we're given a demand function, so you can think of it as a price at which a product is sold. X is the number of units. It's asking for marginal revenue. So there's a problem like this that was in the previous lesson, and it was brought up earlier today about marginal revenue. So marginal revenue is the derivative of revenue. But what is revenue? It's the price times the number of units. Okay, so d of x is first rewritten in this form. So to get to marginal revenue, we need the revenue. So that's x times d of x. So that's what our revenue function is. So marginal revenue would be the derivative of revenue. But here we have x times all of this raised to the 1/2. Once again, this will be, this calls for the product rule So to get your reduction rule of a product rule, P and Q will be the pieces of this product. So the first piece is X, so P prime is just 1. And then the other piece will be this expression raised to the 1/2 power. So then you take a derivative of it. So we have the same expression raised to the minus 1/2 power times the derivative of what's inside here. So that would be 8x plus 5. Oh, that's, I got to label that. That's Q prime of x. So these are all the pieces you need to get a derivative of your revenue function. And we see here how those pieces are put together. So here we have Q times the derivative of P, which is just 1, plus P, that's just X, times the derivative of Q. And we have all of that down here. There isn't really any particularly helpful simplification that can be done here. But what the problem asked for was a marginal revenue when 3 items are sold. So that's X equal to 3. So just go ahead and substitute X equal 3 throughout here. So that's going to be a rather nasty expression to put into your calculator. That will give you this. And it's asking for the answer rounded to 2 decimal places. Here we have 0.116, so we got to round up. So 16.12 is the final answer in this case. So we've seen a few problems like these where you're actually using the product rule, but along in the process of carrying that out, the general power rule is needed. Okay. Now, this problem, compared to the recent ones, is the exact opposite. So we saw some problems where first use a product rule and the power rule is used along the way. Here it is the opposite. Here we have to use the general power rule first, and while carrying it out, because what's being squared here is a product, the product rule is needed to take a derivative of this inner function. So what ends up happening is, so we use a general power rule. Whoops. Oh, wrong problem. Okay. So the 2 comes down. Then we have all of this that was inside here being raised to the first power, but that's just itself. Then you have to take the derivative of what's inside here. Well, that's everything that you see in square brackets. So here we have second function times the derivative of a first plus first function times the derivative of the second. So here we have a general power rule framework. It's just that the general power rule calls for taking a derivative of what's inside here. That needed the product rule. So if you have particularly complicated expressions that are being raised to a power, yes, you go ahead and apply the general power rule first, and then who knows how much work you'll have to do to get a derivative of what's inside here. This depends on what that function is. And in fact, here we see another example of that same thing. So first and foremost, this is a squaring. So we're taking a derivative of this using first the general power rule. So the 2 comes down, we have this unchanged being raised to the first power because we subtract 1 here. And then you have to take a derivative of this whole fraction, and that is what goes over here. But because it's a fraction, the quotient rule is what's needed. So here we have denominator times the derivative of a numerator minus numerator times derivative of a denominator. All of that over denominator squared. So all of that goes off to the side here as part of what's needed for the general power rule. So here we have the squaring of we're raising a quotient to a power rule followed by quotient rule. Whereas if you had a instead of having a quotient raised to a power, if you have functions being raised to powers embedded within a quotient, then the quotient rule is what you use first, and the power rule gets used within that. Okay. Last problem, we've seen problems like these before in terms of finding the equation of a tangent line. It's just now it's with a function, a given function that for which the general power rule is required. So to get the equation of a tangent line, what do you need? You need the slope. The slope of a tangent line is the derivative. So we go ahead and carry that out using the general power rule. So the 2 comes down. Then we have this expression raised to the first power. And then you take a derivative of what's inside here, and that's where the 4x minus 6 comes from. And here what's done here is here's what's done is taking this 2 and just distributing it through here, just to declutter things a little bit. But then you just go ahead and leave it in this form. Now we actually need a number for a slope. So once you have a derivative, you need to plug in the given x value, in this case 1. So we go ahead and work that out, and we get a slope of 44. The other thing you need for the equation of a tangent line, you need to plug the same x value into the original function. So we plug in x equal 1 there, and we get 121. We actually get minus 11, but all that is squared, and that's what gives us positive 121. All right, now that we have all those pieces, we have both the function and a derivative evaluated at x equal 1. We go ahead and get the equation of a tangent line. So this is point slope form. That's easier to work with. So y minus the y value, so here the function value goes here, is equal to the slope, which we use a derivative for, times x minus the given x value. Now x is given to be 1. Now here you actually do have the equation of a line, but Hawks wants it in y equals mx plus b form, or we may have a prompt that says y equals. So we rearrange with 121 over here, multiply through the distributed slope through the x minus x value, and then go ahead and combine everything, and then you're done. So this is what you enter as your final answer, the 44x plus 77. Okay. Questions on any of these? Okay, I will end the recording here. And if anyone has any questions they want to ask of me individually, I'll stick around for that. And otherwise, off you go.